The expression stretched to the limit is an appropriate expression in calculus. We push functions all the way to the boundaries of possibilities. The concept of a limit captures precisely the idea of accessing values that, at first sight, appear to be forbidden or out of bounds. In this video, we look at a range of phenomena that involve getting closer and closer to some kind of ideal point or value. We also make explicit some examples and notation involving infinity, which captures the idea of being free to go on and on. Then we continue on discussing some limit laws that could be used to simplify and evaluate more complicated limits. Slopes of tangent lines to curves are an introduction to this idea of an idealized value. By the way secants behave near the point of intersection of a tangent line to a curve may be enough to tell you what's happening on the tangent line itself. In a previous video, we demonstrated by pure thought and manipulation of symbols that the slopes of secants to the parabola y equals x squared approach the slope of the tangent line, which happens to be 2 times x at the point with input x. We realized that the underlying method works for any smooth curve, leading to the idea of a limit in this notation. LIM is an abbreviation for limit and refers to some limiting value or behavior that is being approached. Let's discuss two similar but contrasting examples. Fx equals x squared minus 1 divided by x minus 1. And g of x equals x squared minus 2 divided by x minus 1. These are both examples of rational functions, ratios of polynomials. In both of these cases, x equals 1 creates a problem in the denominator because trying to evaluate them with x equals 1 means dividing by 0, which is forbidden. Let's do some exploration for x close to 1 for the function f of x. F of 1.1, you can check evaluates to 2.1. F of 1.01 evaluates to 2.01. And F of 0.9999, taking an input very close to it, but just a tiny bit less than 1, evaluates to 1.9999. We seem to be getting closer and closer to 2 by taking our inputs closer and closer to 1. Now, let's try the same thing using the rule for G. which at first appears to be only slightly different. G of 1.1, you can check, evaluates to negative 7.9. G of 1.01 evaluates to nearly 98. Sorry, negative 98. A largish negative number. And G of 0.9999 evaluates to over 10,000, a very large positive number. The behavior of G for inputs near X equals 1 looks wild and unpredictable compared with the apparently stable behavior of F. Let's try to understand why the value of F appear to be converging to 2. In the rule for F, the numerator factorizes as x plus 1 times x minus 1. And we get some kind of cancellation. And the entire fraction simplifies to x plus 1. Throughout, we are assuming that x doesn't equal 1. So the rule y equals f of x is almost exactly y equals x plus 1, the rule of a straight line. The only thing missing is a tiny hole with a rule for f prohibits an input of f of x equals 1. Observe that as x approaches 1 from either side, we slide up and down the line, approaching the hole, while at the same time, the value of y approaches 2 on the y-axis. We use limit notation and say that the limit of f of x as x approaches 1 is 2. This confirms what we anticipated from our exploration. So what about this wild function g? Let's try to simplify the fraction g of x by doing a long division of polynomials, dividing x minus 1 into x squared minus 2. In a few steps, we have the quotient of x plus 1 and a remainder of minus 1. Hence, the fraction g of x can be rewritten as the quotient x plus 1 plus the remainder minus 1 divided by x minus 1. Notice that the first part, x plus 1, is the rule for the line that we saw before in analyzing f. We're also taking away a piece, 1 over x minus 1, which is the rule for a hyperbola. So the rule for g involves a line and a hyperbola. Let's focus on 1 over x minus 1, which is closely related to the simple hyperbola y equals 1 over x. To get the graph for y equals 1 over x minus 1, translate the hyperbola for 1 over x to the right by 1 unit. And note that the line x equals 1 becomes the vertical asymptote. As x approaches 1 from above, using this arrow notation with a little plus sign as a superscript, we see 1 over x minus 1 shoots off towards infinity, which we mean getting arbitrarily large and positive. As x approaches 1 from below, but this time we see 1 over x minus 1 shoots off towards minus infinity, which remain getting arbitrarily large and negative. So we have these two contrasting behavior of 1 over x minus 1 expressed using limit notation and the infinity and minus infinity symbols, which is notation for getting arbitrarily large and positive or negative. Let's combine these with the overall rule for G. As x approaches 1 from above, x plus 1 approaches 1 plus 1 equals 2, which is straightforward. And 1 over x minus 1 becomes arbitrarily large and positive. So that when you take this away from something close to 2, we get something large and negative. We capture this using limit notation. By contrast, as x approaches 1 from below, again, x plus 1 approaches 2. But this time, 1 over x minus 1 becomes arbitrarily large and negative. So that now, when we take this away, we get something large and positive. And we capture this using limit notation. So we have these two concise descriptions of the behavior of g of x as x approaches 1 from either above or below. But there is more information available from the hyperbola. As x gets large, positively or negatively, 1 over x minus 1 approaches 0. We can see the overall effect on the rule for g of x. For large positive or negative x, g of x becomes approximately x plus 1, because the piece minus 1 on x minus 1 is close to 0. The rule for g becomes more and more identical to the rule for the line y equals x plus 1. The farther you are away from the origin, geometrically, that line becomes an oblique asymptote for the curve. We can visualize what happens. Here, the axis, the vertical line x equals 1, and the oblique line y equals x plus 1 dotted in. All of the asymptotic behavior is captured by this green curve in two pieces or branches, which is the graph of y equals g of x. The line x equals 1 is the vertical asymptote, and the line y equals x plus 1 is the oblique asymptote, which becomes a better and better approximation to the curve the further you are away from the origin. You might be curious how we knew to draw it exactly like this, and why, for example, there are no wriggly bits or strange things happening in between the asymptotic behavior. Later on, you will be armed with techniques of curve sketching to determine very precisely the nature of curves like this one by exploiting the derivative and the second derivative. So let's return to both our examples F and G. The graph of F we saw was in fact a line, but with one point missing. As x approaches 1 from either side, f of x approaches 2, captured by this limit statement. And this confirmed our exploration. By contrast, now that we know about the graph of G, we can understand the wild fluctuations. Two statements using limits describe what happens as we approach 1 from either side, explaining the large positive and negative values that we saw. Then we have this other interesting phenomenon that as x gets large, either positively or negatively, the curve is approximated by the straight line y equals x plus 1, which forms an oblique asymptote. There are a number of important limits involving infinity symbols. If you take the simplest hyperbola, the graph of y equals 1 over x that we used earlier, then 1 over x approaches 0 as x gets arbitrarily large positively or negatively, captured by these two statements in limit notation. And the x-axis becomes a horizontal asymptote. By contrast, if x approaches 0 from above, 1 on x or 1 over x gets arbitrarily large and positive. Or if x approaches 0 from below, 1 over x gets arbitrarily large and negative, captured by these two statements in limit notation. And the y-axis becomes the vertical asymptote. If we look at the natural exponential function, we see that e to the x gets arbitrarily large and positive as x does, captured by the statement in limit notation. And notice that we're using the infinity symbol as a value for the limit, even though it's not a number. It's just notation that says that the values becomes arbitrarily large without bound. From the curve, you can see as x gets arbitrarily large and negative, the value of e to the x gets closer and closer to 0, captured by this limit statement. And the x-axis becomes a horizontal asymptote. The contrasting behavior of e to the x as we move along y from the origin in each direction are captured concisely by the limit notation. If we reflect this curve in, we get the curve y equals e to the minus x, and we get the corresponding limit statements, which are mirror images of the two. If we reflect the curve y equals e to the x in the line y equal x, then we invert the function and get the natural logarithm. As x gets large and positive, so does ln of x. but in fact, very slowly. This is called logarithmic growth, in stark contrast to exponential growth. Instead of a rapid explosion, the natural logarithm grows at a snail's pace. And even then, a very, very almost unimaginably slow snail. Finally, we note that as x approaches 0 from above, ln of x gets arbitrarily large and negative, expressed using this one-sided limit. And the negative half of the y-axis becomes a vertical asymptote. We have introduced so many different ideas, all unified by the concept of a limit, which often captures or summarizes some kind of ideal value or behavior in the faraway distance, or evolving or getting arbitrarily close to some prohibited input. All of those can be expressed concisely using limit notation. And various tricks using infinity and minus infinity symbols to indicate arbitrarily large positively or negatively, and plus and minus symbols in the superscript to indicate whether we're approaching something from the right or left, from above or below. We saw examples of rational functions where you can have, for example, a complicated looking rule reduced simply to a straight line with just one point missing. By contrast, another function with almost the same rule but having much more complicated behavior involving an oblique asymptote. I hope you are not already stretched to the limits by all this new material, because I would like to continue discussing some more limit laws with you. Let us now discuss and illustrate several limit laws that enable you to combine simple or known limits to calculate or understand the behavior of new limits that can arise and appear at first sight to be difficult or complicated. The first law states that the limit of a sum is the sum of the limits. The second law says that the limit of a difference is the difference of the limits. The third law says that the limit of a product is the product of the limits. It follows as a special case that the limit of a constant multiple is the constant multiple of the limits. We often say constants come out the front. The fourth law says that the limit of a quotient is the quotient of the limits. Provided, of course, that the denominator is not zero. You can have x approaching some number a from either side, or approaching a number from the right or from the left. These are what we call one-sided limits. We can also have x heading off towards infinity, by which we mean getting arbitrarily large and positive, or minus infinity, getting arbitrarily large and negative. There are a few building blocks, and you can combine them with the limit laws to progress very rapidly in many cases. Firstly, the limit of x as x approaches a is clearly just a. This is confirmed by looking at the graph of y equals x, which I've drawn but made a tiny hole at x equals a, because we are interested in limiting behavior as x approaches a, but doesn't necessarily actually reach a. As x approaches a on the horizontal axis, y equals x approaches a on the vertical axis. The limit of a constant, regardless of what is going on, is just the constant c. This is clear by looking at the graph of y equals c. Again, I've made a hole at x equals a. As x approaches a on the horizontal axis, y is stuck always on c on the vertical axis. If x gets very large and positive, or large and negative, then its reciprocal 1 on x or 1 upon x tends to 0. So that the limit of 1 on x is in both cases is equal to 0. This is clear from the graph, which is a hyperbola. As x moves further and further away from the origin in either direction, the value of y equals 1 over x gets closer and closer to 0. Let's look at some examples. Let's find the limit as x approaches 2 of 2x minus 1. By the second law, it becomes a difference of the limits of 2x and of 1 as x approaches 2, which becomes the limit of 2 multiplied by the limit of x, all take away 1, which quickly becomes 3. You can see the effect of this visually. The graph of y equals 2x minus 1 is just a straight line. And we place a hole in the line corresponding to 2 on the horizontal axis, which x is approaching. However, the hole lines up exactly with the value 3 on the y-axis, which is the limiting value of 2x minus 1. In this case, we can actually fill in the hole with x coordinate 2 and y coordinate being the limiting value as x approaches 2. As another example, the limit of x squared as x approaches minus 2 is by a limit law. The square of the limit of x, which is minus 2 squared, which is 4. This also makes sense graphically. The graph is a parabola. If we put a hole in the graph at -2 on the horizontal axis, which x is approaching, then the hole lines up directly with 4 on the y-axis, the limiting value of x squared. Again, it's as though we can fill in the hole perfectly with x-coordinate -2 and y-coordinate being the limiting value as x approaches -2. Previous two examples are special cases of the general phenomenon. To find the limiting value of the polynomial, simply evaluate it at the input that x is approaching. This relates to a property called continuity, which we will discuss in a later video. As a more elaborate example, consider the limit of this cubic polynomial as x approaches 1. Because the cubic is built up from x and by constants, along with addition and multiplication, we can apply the limit laws to bring the limit inside the expression. This has precisely the effect of evaluating the polynomial at x equals 1, yielding in the answer 2. We don't need to know what the graph actually looks like. In general, if p of x is any polynomial, then the limit of p of x as x approaches a is just p of a. Let's look at a more elaborate example involving a rational function that is a quotient of two polynomials and try to deduce some asymptotic behavior by using the limit laws. Here's a complicated expression. We want to see what happens as x goes to infinity. The leading terms in the numerator and denominator involving x cubed have been circled as they will dominate the expression as x gets large. The remaining bits and pieces involving large powers of x start to look insignificant by comparison with the leading terms when x is large. In the limit, we expect the answer to be unchanged by simply throwing away these lower order insignificant pieces to get the limit of 3x cubed divided by 2x cubed. But then this cancellation, and we are just left with the limit of the constant 3 over 2. So for the reason we expect the answer to be 3 over 2, we expect the answer then to be 3 over 2. For a more thorough or careful analysis, we can do some algebraic manipulation. We'll do that first and then apply limit laws. For a more thorough or careful analysis, we can do some algebraic manipulation first and then apply limit laws. The trick is to first divide throughout everything in the numerator and denominator by the highest power of x that appears. And by this we mean x cubed. This doesn't change the overall value of the expression. But by the limit laws, we can bring the limit inside the expression and see what happens to each of the simple pieces that we have created. And the end result we see turns out to be 3 over 2. This tells us, in fact, that the horizontal line y equals 3 over 2 will be an asymptote to the curve for this particular rational function. So we've made significant progress utilizing limit laws to deal with some quite difficult and tricky limits. We discussed and illustrated how limits respect arithmetic operations. Limits can be brought inside sums, differences, products, and quotients. Thank you very much for watching, and I look forward to seeing you again soon.